In this module, we will focus on one of the most dynamic aspects of today's construction industry, the impact of technology and digital construction. This is where tradition meets transformation, where centuries-old practices of building are being reshaped by cutting-edge innovations. We will start by looking at the overall picture of the modern construction industry and its digital transformation. Then we'll explore the technologies shaping this transformation, including building information modeling, artificial intelligence, robotics, drones, sensors, the Internet of Things, modular and prefabricated construction, and even 3D printing. Along the way, we'll discuss new construction techniques and materials, as well as the opportunities and challenges of adopting these technologies. Finally, we'll consider some real-world case studies that illustrate how digital construction is changing the way we build. This module is designed to help you develop a clear understanding of how technology is influencing construction today, and how it will continue to reshape the industry in the future. Let us begin with an overview of the construction industry in the modern era. Section 1. The modern construction industry and its digital transformation. Construction has always been one of the pillars of human civilization. From ancient stone temples to modern skyscrapers, construction has shaped societies, economies, and cultures. But in the 21st century, construction is undergoing a fundamental shift. For many years, the construction industry was known for being slow to adopt new technologies. Compared to industries such as manufacturing or finance, construction relied heavily on traditional methods. Paper-based drawings, manual processes, and on-site decision-making were the norm. Projects were often plagued by delays, cost overruns, and inefficiencies. However, in recent decades, things have changed dramatically. Several forces have pushed construction toward modernization. Global competition, the need to deliver projects faster and at lower cost. Urbanization, growing populations in cities requiring large-scale infrastructure. Sustainability demands, pressure to reduce carbon emissions and waste. Complex projects, megaprojects that require precision and coordination. Client expectations, the demand for higher quality, transparency, and efficiency. These forces have led to the rise of what is now called digital construction. Digital construction means the integration of advanced technologies throughout the lifecycle of a project, from planning and design to construction, operation, and maintenance. It involves using digital tools to create, share, and analyze information, enabling better decision-making, coordination, and productivity. Digital construction is not about a single technology, but a network of innovations that together transform how projects are delivered. Section 2. Building Information Modeling, BIM. Perhaps the most revolutionary tool in digital construction is Building Information Modeling, or BIM. BIM is much more than just 3D modeling. It is a process that involves creating and managing digital representations of the physical and functional characteristics of a facility. A BIM model is not only a visual 3D model but also a database of information. Each element in the model contains data about materials, dimensions, cost, performance, and maintenance requirements. To understand BIM, imagine designing a hospital. In traditional methods, you would have architectural drawings, structural drawings, mechanical drawings, and electrical drawings, all separate. Coordinating these different plans was complex and prone to errors. With BIM, all disciplines work on a single digital model. If the architect moves a wall, the structural engineer sees it instantly, and the electrical engineer adjusts wiring accordingly. The benefits of BIM include improved collaboration, all stakeholders share the same information. Clash detection, conflicts between systems, such as pipes and beams, can be spotted before construction. Cost control, quantities and costs can be extracted directly from the model. Lifecycle management, the model continues to serve the facility after construction, supporting maintenance and future renovations. BIM has become a standard in many countries, with governments mandating its use for public projects. It is not just a tool but a paradigm shift in how buildings and infrastructure are conceived and managed. Section 3. Artificial Intelligence, Automation, and Robotics. The construction industry is also being reshaped by artificial intelligence, AI, automation, and robotics. AI refers to the use of computer systems that can perform tasks requiring human-like intelligence, such as learning, reasoning, and problem-solving. In construction, AI is being used to Analyze project data to predict risks and delays. Optimize schedules by learning from past projects. Enhance safety by monitoring site activities and predicting hazards. Automation involves using machines to carry out repetitive tasks with minimal human input. For example, automated bricklaying machines can lay bricks faster and more precisely than humans, freeing workers to focus on skilled tasks. Robotics takes automation further. Robots are now being developed to perform demolition tasks in hazardous environments. Carry out precision welding or concrete printing. Inspect hard-to-reach areas of structures. These technologies can increase productivity, improve quality, and enhance safety. But they also raise questions about workforce adaptation, training, and the role of human labor in a digital age. Section 4: Drones, Sensors, and the Internet of Things, IoT. Another powerful trend in digital construction is the use of drones, sensors, and the Internet of Things. Drones provide aerial views of construction sites, allowing project managers to monitor progress, survey land, and create 3D site maps quickly and affordably. They can capture data that would otherwise require costly equipment or risky manual inspections. Sensors are devices placed on equipment, structures, or even workers to collect real-time data. For example, sensors can monitor concrete curing times, track the location and use of machinery, measure structural loads or vibrations, ensure workers are wearing safety equipment. The Internet of Things, IoT, connects these sensors and devices into networks that feed data to centralized systems. This enables smart construction sites where managers can track everything from equipment efficiency to worker safety in real time. The result is improved decision-making, enhanced safety, and reduced waste. Section 5: Prefabrication, Modular Construction, and 3D Printing. In addition to digital tools, new construction methods are transforming the industry. Prefabrication refers to manufacturing building components in a factory and then transporting them to the site for assembly. Modular construction takes this further by producing entire building modules, such as bathrooms, hotel rooms, or apartments, in factories. These modules are then assembled like building blocks on site. The benefits include faster construction times, higher quality, since work is done in controlled environments, reduced waste and energy consumption, improved worker safety by reducing on-site labor. 3D printing, or additive manufacturing, is another breakthrough. Using specially formulated concrete or other materials, 3D printers can construct entire walls or even small houses layer by layer. This method reduces material usage and opens the door to innovative architectural designs. Together, prefabrication, modular construction, and 3D printing represent a move toward more industrialized, efficient, and sustainable construction. Section 6: Innovation in Construction Materials. Technology is not just about digital tools, it also involves innovation in materials. Some of the most exciting developments include self-healing concrete, concrete that uses bacteria or chemicals to repair its own cracks, extending its lifespan. Transparent aluminum and advanced glass, materials that are strong yet allow light transmission. Nanomaterials, materials engineered at the microscopic level to have enhanced strength, durability, or insulation properties. Smart materials, materials that respond to environmental conditions, such as windows that adjust their tint based on sunlight. These materials have the potential to create buildings that are stronger, more energy efficient, and more adaptable to changing conditions. Section 7: Challenges and Opportunities of Technology Adoption. While the promise of digital construction is great, adoption is not without challenges. Some of the key challenges include high initial cost. Technologies like BIM, robotics, and IoT require significant investment. Training and skills gap. Workers and managers need new skills to use digital tools effectively. Resistance to change. Some professionals prefer familiar methods and are slow to adopt new practices. Data security. With digital models and connected devices, cybersecurity becomes a major concern. On the other hand, the opportunities are enormous. Increased efficiency and productivity. Greater accuracy and reduced errors. Enhanced safety and sustainability. Global competitiveness for firms that embrace innovation. Thus, the future of construction will depend on how well the industry balances these challenges and opportunities. Section 8. Case Studies in Digital Construction. To bring these ideas to life, let us look briefly at some examples. In Singapore, BIM is mandated for large public projects. This has led to improved project coordination and reduced delays. In China, 3D printing has been used to construct multi-story buildings, showcasing the potential for rapid, affordable housing. In the United States, drones are widely used in large infrastructure projects for surveying and monitoring. In Europe, modular construction is being applied in housing projects to address urban housing shortages quickly and sustainably. These examples show that digital construction is not a distant dream but a present reality, reshaping projects worldwide. Conclusion of Module 1. In this module, we have examined the role of technology in contemporary construction. We saw how the industry is transforming through digital tools like BIM, AI, robotics, drones, IoT, prefabrication, modular construction, 3D printing, and new materials. We also considered the challenges and opportunities of adopting these innovations and looked at real-world case studies. The message is clear: technology is no longer optional in construction, it is essential. The firms and professionals who embrace it will lead the industry into the future, while those who resist may be left behind. In the next module, we will shift our attention to another critical dimension of contemporary construction: sustainability and procurement. We will explore how environmental, social, and economic factors are reshaping building practices, and how procurement strategies influence project success. That concludes Module 1.